Welcome to the deep dive. Today we're tackling a really intriguing area, pushing the forefront of large language model capabilities.
Yeah, it's fascinating stuff.
For a while now, the main way to make these models smarter has been to simply scale them up, adding more and more parameters.
Right.
Think of DeepSeek V3, right? With its massive 672 billion parameters.
Huge numbers.
But this approach brings significant challenges, especially when it comes to the sheer storage space required. It makes deployment tricky outside big data centers.
That's right. And beyond just storing these behemoths, we face hurdles during inference, the actual, generating text or code part. Even these incredibly large models can require a surprisingly high number of generated tokens for what seem like straightforward reasoning tasks.
Like how many?
Well, the research we're diving into today mentions examples where models might generate up to 900 reasoning tokens for relatively simple problems.
900, wow. That translates to a lot of computation and time just to get an answer.
Exactly. Significant cost there.
Exactly. So the core question we're exploring today is there a more universally applicable and crucially more efficient method to scale these models without incurring these enormous costs in terms of space and inference time?
That's the million-dollar question, isn't it?
And our source for this deep dive, a fascinating recent paper, directly addresses this. Their inspiration comes from an unexpected place, classifier-free guidance, or CFG.
CFG. Yeah, that's well established in diffusion models, the ones used for generating images, audio, that sort of thing.
Right. So what's the link there?
Well, what's particularly innovative about CFG is its use of not just one, but typically two forward passes during inference.
Two passes.
Yeah, it's kind of like the model is examining the problem from two slightly different angles. It does a standard pass, gets an output, and then it processes a modified version of the input, basically a slightly worse or, let's say, differently conditioned input to get a second output.
Okay.
And then these two outputs are intelligently combined, often resulting in a better final output than you'd get from just a single pass alone.
And this sparks a really interesting idea, right? The researchers behind this paper questioned whether CFG's effectiveness stemmed not just from the clever combination, but maybe more fundamentally from the increased computation involved those two forward passes.
Exactly. That's the jump they made.
Which led to their central hypothesis, which feels quite novel. Can we significantly enhance a model's capability by scaling parallel computation, even if we keep the number of parameters relatively stable?
Right. Instead of just making the model bigger.
It's almost like saying, instead of building a bigger engine, let's explore adding more smaller engines that work simultaneously.
A nice analogy. And to rigorously test this concept, they introduce a proof of concept framework they've named parallel scaling, or ParScale.
ParScale, okay.
The fundamental idea behind ParScale is quite elegant, really. Imagine taking your input and attaching several different but crucially learnable short sequences of information. They call these prefixes to it.
Learnable prefixes, got it.
You then feed each of these slightly modified inputs into the model at the same time, in parallel. So if you have key parallel streams, you are effectively running the original model p times concurrently on slightly different versions of the input.
Okay, let's maybe unpack that aggregation part a bit more. We now have these p-parallel outputs. How are these combined into a single coherent final answer?
Yeah, this is where the dynamic weighted sum comes into play, which is another key innovation here, instead of just, say, averaging the outputs.
Which would be the simple way.
Right. ParScale employs a small neural network, specifically a multi-layer perceptron, or MLP, to learn how to dynamically assign importance, or weights, to each of those p parallel outputs.
So it learns which stream is best for each step.
Essentially, yes. For each token being generated, the model actively decides which of the parallel streams' predictions are most relevant and weighs them accordingly to produce the ultimate result.
That's clever.
And what's particularly ingenious is that this entire process heavily leverages and reuses the vast majority of the original large language model's parameters.
Reusing parameters, that's the key part, isn't it? Because the overhead.
Precisely. The additional parameters introduced for these prefixes and the weight aggregation mechanism are remarkably small, around a mere 0.2% increase per parallel stream, according to their analysis.
Only 0.2%, that's tiny.
Very small. And their initial pivotal experiments strongly indicated that it's the sheer number of parallel computations, that p factor, that exerts the most significant influence on the observed improvements.
Okay, so it's really about the computation, not adding tons of new weights.
That's what the early science pointed towards, yeah.
Here's where it gets really interesting, I think. This research isn't just presenting a new trick. It's also engaging with a pretty fundamental debate in machine learning. What truly dictates a model's capacity?
Right, the age-old question.
Is it primarily the number of parameters, the sheer size, or is it the amount and nature of the computation we apply? Historically, we've largely scaled both together, haven't we?
We have, yeah, making it hard to separate their effects.
So the researchers proposed that ParScale, along with the novel scaling laws they derive from it, might give us a completely new lens to examine this critical question.
Exactly, and they specifically draw that inspiration from classifier-free guidance, which, as we discussed, involves taking an input and a bad or differently conditioned version, provisting them, and then aggregating the two outputs. ParScale, in essence, represents a significant generalization of this idea, extending it to P different learnable transformations, combined with those dynamically learned aggregation weights.
Right, so we understand the inspiration. Now let's maybe dive into the more specific implementation details. How does ParScale actually work under the hood?
Well, as we touched on, for that crucial input transformation step, they settled on using prefix tuning.
Prefix tuning.
Think of it as adding a few extra learnable virtual words or embeddings right at the beginning of the input sequence. Critically, these added prefixes are distinct for each of the P parallel streams.
Okay, so each stream gets its own little nudge.
Kind of, and technically within the transformer architecture, this is achieved by using different key value caches.
The KV cache, right? The model's short-term memory for the sequence.
Exactly. So by having different KV caches for each parallel stream, you're essentially giving each stream a slightly different working memory of the input it's processing.
Okay, that makes sense.
And then for the aggregation of these P parallel outputs, they use that dynamic weighted average mechanism we mentioned. They basically concatenate all P output vectors and feed them into that small MLP.
And the MLP spits out the weights.
Right. It outputs the learned weights used to combine the individual predictions. The paper highlights that this weight generation part accounts for that very small increase in total parameters per stream.
The 0.2% again.
Yeah. And importantly, their initial pivot experiments where they tried various input transformation methods like LoRa and BitFit and different aggregation techniques strongly indicated that P, the number of parallel computations, was by far the most influential factor on performance.
So the specific way you tweak the input matters less than just doing it multiple times in parallel.
That seemed to be the main finding from those early tests, yes.
Okay, so they've established this ParScale method. But how do they demonstrate that scaling computation in this parallel way can achieve comparable effects to just making the model bigger, adding more parameters? This is where the theoretical analysis comes in, right?
Precisely. They needed a theoretical grounding. Their framework builds upon the well-established concept of ensembling.
Combining multiple models.
Right, combining predictions to get a better overall result. A fundamental principle there is that you get the biggest gains when the individual models in your ensemble show diversity. They make different kinds of errors.
Okay, diversity is key.
So the researchers then extend the existing chinchilla scaling law.
Ah, the chinchilla law. That relates model size and training data to performance, right?
Exactly. It elegantly describes that empirical relationship. They formally present it as lemma 3.1 in the paper, the mathematical form.
Okay, so chinchilla is the foundation. How do they then adapt this for their parallel scaling?
That leads us to Proposition 1, which presents their arrived theoretical formula for the parallel scaling law. It's a bit mathematical, but at its core.
Bear with us.
It expresses the training loss L of a ParScale model with P streams and N parameters as a function of NP and a crucial term they define as diversity.
Diversity, okay.
Mathematically, this diversity term is derived based on rho.
Rho.
Yeah, rho represents the correlation coefficient between the relative errors or residuals of the predictions generated by the different parallel streams.
Okay, that's quite a bit to digest. Can we break down what this diversity and rho actually tell us in simpler terms? Like, what does the correlation of errors mean practically?
Absolutely. Think of rho as just a measure of how similar the mistakes are that the different parallel streams make.
Okay.
If raw is 1, it means all the streams are making basically identical errors.
So no benefit from multiple streams then?
Exactly. In that case, your diversity term becomes minimal, and their formula essentially just simplifies back to the original chinchilla law. You haven't gained anything from the parallelism.
But presumably E or I isn't usually 1.
Right. The researchers point out that even introducing a small degree of randomness in how the initial prefixes are set seems to be enough to avoid this perfect correlation.
Got it. So if raw is less than 1, we start to see the advantages of parallel scaling emerge.
Exactly. When raw is 0, it signifies that the errors from different streams are completely uncorrelated or independent. They're making different kinds of mistakes.
Which is good for ensembling.
Precisely. In this ideal scenario, their theoretical analysis reveals that the training loss exhibits a power law relationship with P, meaning the loss decreases quite substantially as you increase the number of parallel computations.
A power law, that's a strong relationship.
It is, and even more interestingly, if ROD happens to be negative,
Negative correlation, how does that happen?
it suggests the different streams are making errors in somehow opposite directions. This can lead to an even greater reduction in the overall loss.
Wow.
And the researchers propose this might be a key reason why classifier-free guidance works so well. By using both a good and a bad input, you're essentially encouraging the model to explore more diverse perspectives, potentially leading to negatively correlated errors.
That's a fascinating potential explanation for CFG's success. So the fundamental takeaway from this theoretical analysis is, what?
The takeaway is that scaling parallel computation by a factor of p is, at least in theory, equivalent to scaling the model's parameters by a factor that incorporates both p and this diversity term.
That's a really significant theoretical insight. Suggests computation scaling can substitute for parameter scaling to some extent.
It is indeed a potential equivalence. And to rigorously validate this theoretical framework, they then proceeded with expensive empirical experiments. They needed to see if these predictions hold up in practice.
Right. Theory is one thing, practice is another. And how did they go about conducting these experiments? What types of data did they use for training?
They performed pre-training experiments on two very large, well-known data sets. First was Stack V2, specifically the Python subset.
So code and reasoning focused.
Exactly, heavy on code and logical reasoning. The second was the pile.
The pile, much more general, right? Common sense knowledge.
Right, a more general purpose corpus designed to evaluate common sense knowledge and memorization across a broad range of topics. Using these two distinct types allowed them to see if parallel scaling helps differently for different kinds of tasks.
Makes sense. And what were the key findings when they trained models with varying numbers of parallel streams P on these datasets?
They observed a consistent and clear trend. As they increased P, the number of parallel streams, they saw a corresponding and predictable decrease in the training loss.
Okay, so more parallel streams, lower loss. Did it follow a pattern?
Interestingly, yes. The improvements appeared to follow a logarithmic pattern. As you add more streams, the benefit of each additional stream gets a bit smaller, but it keeps improving.
A log relationship.
Which led them to propose a practical parallel scaling law, presented as equation 5 in their paper. This formula basically relates the loss L to parameters n and parallel streams P through a log term involving P plus some fitted constants.
And did this practical scaling law actually match their experimental results? Did it fit the data well?
Remarkably so. Figure 2 in the paper shows this really clearly. It plots their experimental results alongside the fitted scaling law curves. They got a very high degree of agreement for both Stack V2 and the pile.
How high?
R-squared values reaching as high as 0.998.
Wow, nearly perfect fit. That's strong empirical support.
It really is. It backs up the idea that there's a quantifiable, predictable relationship between parallel computation and model performance. They also noted something interesting about one of the fitted constants, K.
K, what does that represent?
K essentially quantifies the benefit you get from increasing parallel computation, and they found K was significantly higher for Stack V2, the code dataset, compared to the pile, 0.33.
Okay, so a higher K for Stack V2, the reason-heavy dataset. What's the implication there?
The researchers interpret this difference as suggesting that tasks that are more reasoning intensive, like code generation, tend to benefit more from increased parallel computation compared to tasks relying more heavily on memorization, like those in the pile.
That makes intuitive sense.
And this observation leads them to propose a really thought-provoking conjecture.
Which is?
That the number of parameters in a model might primarily influence its ability to memorize information.
Okay.
Whereas the amount and nature of computation, particularly this parallel computation shown by ParScale, might be the more critical factor in enhancing its reasoning capabilities.
Parameters for memory, computation for reasoning. That's a very clean potential separation.
It is. They point out it aligns with some recent findings on inference-time scaling, but they emphasize their work provides a more rigorous, quantitative framework for assessing these relative contributions.
That's a really significant potential insight. The paper also includes a conceptual figure 3, illustrating predicted loss contours. What does that figure show us about the trade-offs?
Right. Figure 3 gives you a visual representation of this idea. It suggests you can potentially achieve similar levels of model performance either by increasing parameters the traditional way or by increasing parallel computation with ParScale.
So different paths to the same performance level.
Exactly. The contour lines map out different combinations of model size, parameters, and number of parallel streams that result in roughly the same training loss. It visually highlights that potential trade-off.
Which means
It means in scenarios where resources like memory or latency are tight, you might get comparable performance from a smaller base model just by cranking up the parallel computation via ParScale.
very interesting implication for resource constraints. And their investigation wasn't just about pre-training loss, right? They looked at actual downstream task performance.
Absolutely. Can't just look at loss. Tables 2 and 3 in the paper show the average performance on various code generation benchmarks like Human Evil Plus and MBPP Plus A after pre-training on Stack V2,
Okay.
and also on a suite of general language tasks after pre-training on the pile. The results consistently show that for models with roughly the same parameters, increasing P through ParScale leads to tangible performance improvements across these diverse downstream tasks.
So it's not just lowering loss, it's making the models actually better at doing things.
Correct. It further validates the practical effectiveness of parallel scaling beyond just the initial training phase.
So we've established that parallel scaling looks effective, theoretically sound, empirically validated, helps downstream tasks. But what about the cost, particularly during inference when you're actually using the model?
Yeah, the practical cost, this is critical. While flops floating point operations per second are sometimes used.
The usual metric.
Right. But the researchers argue, correctly I think, that for transformers, memory access and latency, the actual time it takes to get an output are often the real bottlenecks during decoding.
Memory dictates the hardware, latency affects user experience.
Exactly. Those are often more important in practice.
And how does ParScale stack up against traditional parameter scaling when we look at memory and latency?
Figure 4 in the paper offers a very compelling comparison here. It looks at how GPU, memory usage, and inference latency change as you scale up either parameters or parallel streams with ParScale across different batch sizes.
And the results?
Quite striking. For instance, at a batch size of just 1, which is common for many real-world uses, especially on edge devices.
Like on a phone.
Exactly. Scaling a 1.6 billion parameter model to use 8 parallel streams with ParScale resulted in a 22 times smaller increase in GPU memory compared to scaling parameters to get similar performance.
22 times less memory increase. That's huge.
It's a dramatic difference. And the latency increase was also significantly less, about 6 times smaller in that same scenario.
Wow. So much more memory efficient and faster too relative to parameter scaling for the same performance boost.
That's the finding, yeah. The researchers really emphasize that this inherent memory efficiency makes ParScale particularly well suited for deployment on resource-constrained edge devices.
Smartphones, cars, robots, places where memory is really limited.
Exactly, and where batch sizes are often small. As we move towards more on-device AI, this memory efficiency could be a genuine game changer, enabling things that just weren't feasible before with huge models.
So ParScale looks promising for training, but maybe even more promising for practical, scalable deployment. The paper also explores scaling the training data, right? Not just the model or computation.
Yes, their initial scaling law experiments were limited, computationally, to about 42 billion tokens of training. To see how ParScale holds up at a more production-like scale, they ran experiments training a 1.8 billion parameter model on a massive 1 trillion tokens.
1 trillion. Okay, that's serious scale. How do they do that?
They used a 2-stage training strategy, started with standard pre-training for a while, and then in the later stages, they switched on the parallel scaling technique. The data was a mixed general text, math, code.
And what happened during this massive training run?
Well, figure 5 shows the loss curve. Pretty standard stuff there. More importantly, table 4 compares the performance of these 1.8B models trained on 1T tokens using different numbers of parallel streams P.
How do they compare?
They even included strong baseline models of similar size for comparison. The results clearly show that increasing P with ParScale led to significant consistent performance gains across general knowledge, math, and code tasks, often enough to outperform those strong baselines.
So even at massive data scale, adding parallel compute helps significantly.
That's what the data suggests, yeah.
And did they also look at instruction tuning these ParScale trained base models?
They did. Took the base models, pre-trained with different p-values, and then did instruction tuning to align them better with human instructions. They also increased the sequence length and adjusted the rope base during this phase.
And the results, did ParScale's benefits carry over?
Yes. Table 5 shows the results on benchmarks like IFEVL, MMLU, GSM-8K. Again, consistent, often substantial performance improvements as the P used during pre-training increased, so the benefits seem to persist through fine-tuning as well.
That's really comprehensive. It's particularly interesting they even tried applying ParScale to an existing off-the-shelf model, QQuen 2.5. How did that work out?
Yeah, that's a cool experiment. They took QQuen 2.5, a 3 billion parameter model already trained on a huge 18 trillion tokens.
Yeah.
Whoa. And tried two things. First, continual pre-training. Just kept training it on the Pile and Stack v2 datasets using ParScale. Even starting from that powerful base, figures 6a and 6b show they still got a noticeable drop in training loss.
So you can potentially improve even already huge, well-trained models.
Seems so. Second, they tried parameter-efficient fine-tuning, PEFT.
PEFT. So freezing most of the model.
Exactly. Froze almost all of Quen 2.5's original weights and only tuned the small number of parameters added by ParScale, the prefixes, and the weighting MLP.
And
Figure 6c shows that even with this super efficient tuning, they got significant improvements in code generation performance. It really highlights the adaptability of ParScale.
that's truly compelling. The fact you can take an existing model, freeze it, add ParScale, tune only that tiny bit, and get better performance. That seems incredibly practical.
Indeed. And it also points to another potential advantage, the flexibility to maybe dynamically adjust the number of parallel streams depending on the application.
Oh, interesting. Use fewer streams for speed, more for accuracy.
Exactly. Maybe fewer streams for low latency needs, more streams when top accuracy is paramount, all using the same base model. That's a possibility this opens up.
Now, of course, this work doesn't exist in a vacuum. The paper discusses related research. How does ParScale fit into the broader landscape? How does it compare to other ways of boosting LLM capabilities?
Right. Context is important. They connect it to several areas. Firstly, inference-time scaling methods like chain-of-thought prompting.
Right, making the model think more at inference time.
Yes, but they highlight a key difference. ParScale increases computation through parallelism, whereas chain of thought is sequential, step by step. That sequential nature can sometimes be less efficient, maybe even lead to overthinking.
Okay, parallel versus serial computation. What else?
They also compare it to other parallel techniques like beam search or proposal verifier methods. They note these often have limitations, maybe only work for specific tasks or need specialized training data. ParScale seems more general purpose.
What about other multi-computation approaches, like CFG itself?
They definitely acknowledge the link to CFG and its NLP adaptations, but they stress ParScale's advantage of leveraging scaling during training, not just as an inference time heuristic. They also frame ParScale as a novel kind of model ensembling.
But where the ensemble members share almost all parameters.
Exactly. Unlike traditional ensembles with independent models, their appendix experiments even suggest it's really the amount of parallel computation that matters most, more than the specific technique used to differentiate the input streams slightly.
And how about things like latent space reasoning?
They contrast ParScale with that too, suggesting ParScale is less invasive, generally easier to integrate with existing pre-trained models without needing deep architectural changes.
It certainly sounds like ParScale carves out a unique and pretty promising niche. But like all good research, it probably raises as many questions as it answers. What open questions or future directions does the paper mention?
Absolutely. Good research always opens new doors. One key contribution is trying to quantitatively separate parameter effects from computation effects. But they readily admit theoretical questions remain.
Such as?
Like, why does the diversity between streams seem to follow that logarithmic relationship with p? Could performance gains sometimes scale faster than logP? Are there upper limits to how much benefit you get from just adding more and more streams?
Theoretical bounds and relationships. Makes sense.
They also mention the two-stage training strategy standard pre-training, then ParScale. What's the optimal point to switch? That's an open, practical question.
Finding the sweet spot.
And finally, they suggest exploring combining ParScale with mixture of expert MOE architectures.
Ah, MOEs. Those are parameter heavy, but can be latency friendly, right? Kind of the opposite trade-off to ParScale.
Exactly. MOEs are memory heavy, latency okay. ParScale is memory light, latency increases with P. They have complementary strengths, so combining them could be a really interesting, potentially powerful direction for future work.
That does sound promising. The paper also has a massive appendix section, right? Any key highlights from there worth quickly mentioning?
Definitely. It's packed with details. Appendix A dives deeper into implementation specifics, different input transformations, prefix tuning, LoRa, bitfit, output aggregations, dynamic weighted sum with label smoothing. Table 6 there really reinforces that the dynamic weighted sum works well, and that P matters more than the specific input tweak method.
Okay,
Appendix B has the full mathematical proof for Proposition 1, the theoretical scaling law, important for the rigor.
good for the mathematicians.
Appendix C lays out all the training hyperparameters and model architectures in detail. Appendix D has a small experiment suggesting ParScale might help mitigate overfitting, which is interesting.
Overfitting too, okay.
Appendix E details the parametric fitting process for the scaling laws with lots of tables, 815, showing the fitted parameters. Appendix F has more training loss curves, figure 8.
Lots of data backing things up.
For sure. Appendix G lists all the downstream datasets and has tons of detailed results tables, 1629. Appendix H compares ParScale directly to beam search, table 30, showing ParScale performing better, especially at higher parallel streams.
Better than beam search? Interesting.
And finally, Appendix I has visualizations, tables 31, 33, showing which parallel streams contribute most at different points in generation. It shows an interesting locality pattern.
That's a tremendous amount of supporting evidence. So to try and synthesize all of this, what are the core innovations and the biggest takeaways from this deep dive into parallel scaling?
I'd say the central innovation is ParScale itself. It's a novel, efficient way to boost LLM capabilities by scaling parallel computation with minimal parameter increase.
Efficiency through computation, not just size.
Right, and their research provides compelling evidence, both theoretical and empirical, challenging the idea that capacity is only about parameters. It suggests computation, especially parallel computation, plays a huge role. They've even quantified this relationship with a practical scaling law.
And the practical benefits?
Huge potential for memory-constrained environments like edge devices, significantly lower memory overhead compared to parameter scaling for similar performance gains.
The 22x figure really stands out there.
It does, and perhaps most fundamentally, their findings point towards that potential functional split. Parameters might be more crucial for memorization, while computation, especially parallel computation like ParScale, seems key for enhancing reasoning skills.
So given these findings, it really prompts us to reconsider how we approach building smarter AI. Will we see this greater emphasis on clever computational strategies, maybe working alongside, or even sometimes instead of just building bigger and bigger models?
It certainly raises that question, doesn't it? Especially as AI gets woven deeper into our daily lives and the devices we use every day. Will computational ingenuity become just as important, if not more so, than raw scale?
It definitely provides a wealth of new perspectives to consider. Thanks for joining me for this deep dive.